Okay, we'll start from the basics first module. So just I will tell you what we have completed and which are the parts which are important for your first module. Okay, so now, so in the first module we have discussed about 1 minute. You know, ಮಾಮೂಲಿ ಕೇಳ್ದಂಗೆ ಕೇಳ್ದ ಅಷ್ಟೇ, ಪ್ರಿನ್ಸಿಪಲ್ ಬಂದಿರಲಿಲ್ಲ. ಎಲ್ಲರಿಗೂ ಬಂದಿದ್ದ, ಒಂದು ಶಿಕ್ಷಣ ಅದೇ ಮಾಮೂಲಿ ಅದೇ ತರನ ಕೇಳ್ದ ಈಗ ಅಷ್ಟೇ. ಮೇಡಮ್ ಜೆ ಓಕೆ, ಕ್ಲಾಸ್ ಇದೆ ಈಗ. ಓಕೆ, okay, we discussed about the risk design philosophy. So we discussed about the ARM design philosophy and we discussed embedded system hardware. Just I am telling which are the parts that are important for your examination point of view as well as your career also, because in the future when the IoT comes into the picture in the real time world, so your ARM plays a very important role. So that is why you should have a full exposure towards the ARM processor. Okay, so now you should know whenever you are doing something means what you should know the basics properly. So that's what you are going to study the ARM. So now we have discussed about the registers which are supported by the ARM instruction, and inside the register we have discussed about the banked register. Then we discussed about the current process status register. Okay, so current process status register we discussed. So then we have discussed about the different components of your CPSR, that is different fields of your CPSR, like we have discussed the flags, status, extension and control. So what are the different bits you are going to have in your control, and what are the bits you are going to have in flags. So since the status and extensions are used for the future purpose. Okay, so we discussed about the pipelining. So we discussed for three ARM processor, that is your ARM 7 ARM 7 processor, 3-stage pipelining. Your ARM 10 is ARM 9 is going to support 5-stage pipelining, and your ARM 10 is going to support 6-stage pipelining. Now there are a number of processors. ARM 13 is there, ARM Cortex is there now in the present market. So there they are going to support you up to 13-stage pipelining. So for your syllabus purpose, when that particular test was written, so it's only up to ARM 10. So that is, it is going to support you up to 6-stage pipelining. Okay. So after that, when we discussed about the core extensions. So in that core extensions, we discussed the 4 different fields. That is the 4 different parts of your core extension. 4 different parts of your core extensions are, it is nothing but cache and tightly coupled memory, so memory extensions and coprocessor we discussed. Okay, so now next we are going for the ARM instruction. Okay, so next we will go with the ARM instruction. What are the different type of instruction your ARM supports? So we are going to do your lab programs and your ARM instruction set simultaneously. Just I will go through some of the instructions in the beginning. Later, once I complete some of the instructions, which you, when you understand those instructions, we'll start writing the program on that particular instruction under Keel software. Okay, so now when it comes to the ARM instruction, so what is different processor is will be having the different types of instructions it is supported. Okay, so now whenever the new revisions will be made, so whenever new revision is nothing but what, when you are updating your processor. So like if you take the operating system, initially we had Windows 95 was there initially, then the Windows 2000 came, then Windows 2003 came, then Windows XP came, and Windows 7 came. Now we are Windows 8 came. So after that, when we are going with Windows 10 right now. So this is nothing but your upgradation. That is a revision what has been happened in the era. So in the generations, how that particular revisions has been taken place. So here also you are going to have a different set of instructions. Okay, so whenever you are going to discuss about the instructions, always all instructions will be upward compatible. So upward compatible means what? So whatever the instructions it is supported by the lower version, again those instructions will be supported by the higher version. Okay. For example, we have discussed ARM7 and ARM9, right? So now, whatever the instructions it is supported by ARM7, the same instructions will be supported by ARM9. Okay. So, but it is not the downward compatible. So, in the downward compatible, what it will happen is whatever, because when the revision is been made, what will happen? So, in the some of the additional instructions will be given in your ARM9. Okay, so it will support some additional instructions or some extra features they are going to provide. So for those particular extra features to be incorporated, you will be having some instruction. Okay, so now that won't be a downward compatibility, or it won't be having the backward compatibility. That means what? Whatever the additional feature you are going to have that particular ARM9, for example, so some of the instructions will be extra added so to that particular processor, so that won't, those instructions will not be supported by your ARM7. That is what it means. Okay, so now here whenever we are illustrating the processor operations with some of the expressions, so we will discuss that what are the different pre instructions and post operation and pre operations, what it is going to have. So that means one instruction you are going to have, so what are the different value, because whatever the value you are going to execute with respect to the instruction, from the first module we have understood that whatever the operation we are going to perform, we have to perform the operation on register only, because you cannot manipulate the data directly in memory. So for that particular reason, what will happen? First, we have to bring the data from the memory to the register, and you have to have the instruction that which will bring the data from the memory to the register. So after bringing the data from memory to the register, you have to execute the instruction on register. So that if you have the add instruction means what? I cannot do the memory operation there. So I cannot send the operand itself as memory. So but first the data has to be moved from the memory to the register, and on the register you have to add it. For example, I will load the data from your from X memory location to R1 register. I will load the data from your Y memory location to R2 register. Then I'm going to add it. So then I'm going to add the instruction which is to add instruction I'm going to make use. By using the add instruction, what I'm going to do is I'm going to add the contents of R1 and R2. Okay, after adding R1 and R2, I can store the added value into some of the R1 or R2 also, or if any other free registers are there, then I can store that particular value in that particular register. So that's what it is going to tell all about. Okay, so now when it comes to the ARM instruction set, so since we are ARM is going to have the assembly language programmer, so whatever the board you are going to use, ARM board we are going to use in your lab, so that you are going to discuss, that we are going to discuss in the lab when you start with your hardware part, because since it is in online we are not able to use the hardware. So when since we are going to learn only about the software part now, so I will share the software also, the compiler, so that you can execute in your home also. Okay, so as and when I'm doing the lab programs, here part is the software part. So that particular part, once the instructions is completed, I will start executing the programs here. Once I start executing the program, you just similarly you practice in your home. Okay, so now when you're going to have the ARM instruction set, so as I told you already that, so it is will be having the ARM development board. So some board will be there, which will be developed by ARM, or so it will be having the ARM emulator. So as the name indicates, ARM emulate. So that means whatever the emulator in the software you are going to do, so it will be having the exact feature of your ARM board. So some emulators are there in the market where you have to purchase that one. So it is a paid version. So in those particular ARM emulator, what it is going to do? So in the hardware, how it is going to work? If you are writing some program, if it is executing that particular program, the same functionality will be there in the software also. So what is the output you are going to get? So that illusion will be there when you are working in ARM emulator. So illusion, what you are going to get when you are working in real-time hardware, the same illusion you are going to get when you are working in ARM emulator. Okay, so now when you are going to have the ARM instruction set, so basically we discussed about three instruction set, I think. So what are they? Anybody remembers? What are the three types of instruction set? So anybody remembers what are the three instruction set which we have discussed? Your ARM instruction ARM 7 is going to support three different types of instruction. So first is your standard ARM instruction set. As I told you that your standard ARM instruction is going to have 32-bit in size. Okay, so these are 32-bit instruction. That means each instruction, when you are writing some code, that is when you are writing some assembly language, first that particular assembly language has to be converted into the binary code, right? So how the compiler is, when you are processing, the processor will understand only binary value. Okay, so now even if you write in C program also, the compiler, what it will do, the compiler will uh, translate your high level language to low level language. So now what that means, so it will convert your high level language which you are written in C program to the machine level language. So here you are going to have the assembler here, because you are going to write in the assembly level language. So now in between assembler will come. So your high level language will be converted to assembly level language. Then assembly language, whatever I'm going to write in your compiler, in the kill compiler. So that assembler which will be there, that particular assembler is going to convert your assembly language to the binary language. So why? Because finally your processor can understand only binary value. So that means that is the machine language which you are going to have. So your processor is going to understand only the binary values. So that is how it is going to be stored. So now if we are going to make use of the ARM instruction set, for example, is that so now if you are going to make use of ARM instruction set, for example, so your assembly language one instruction is converted into 32-bit instruction. When we are discussing about the memory, all memories which you are going to have, that will consume only 8-bit of data. So that means if it is 32-bit means what? How many memory you require to store one instruction? How many memory you require to store one instruction? If each memory location consumes 8 byte of data. So the total ARM instruction set is 32-bit, which is 4 bytes. Now each memory location can store only 1 byte of data. Each memory location can store only 1 byte of data. So when you are going to have, how much memory is required to store one instruction? Can you have the answer? How many memory location you require to store one instruction if you are using the ARM instruction set? Since ARM instruction set is a 32-bit instruction, how many bytes you require? Can you tell? Can you people tell that how many instructions you require? Are you sleeping or what? I want the answer from your side. Hello? Kushi? Kirtana? Mohammed?
Yeah.
So if I have the memory, okay, each memory is going to consume 1 byte of instruction. Okay, it's going to store 1 byte of data, for example. So if you are using the ARM instruction set, the ARM instruction will support 32-bit of instruction. That means whatever the instruction is there, that will be converted into 32-bit, that is 4 byte instruction. So how many memory location is required to store these 4 bytes? If one memory location is going to store 1 byte of data,
4, sir.
yeah. So now each instruction is going to store 4 bytes of instruction. Okay, so that whatever the conversion it is going to have, so that it contains the 4 bytes. Now if you take the same instruction set, if you are running in thumb instruction mode, so now what is the compressed form of the instruction set now we are going to have? So it is nothing but your subset of the full ARM instruction set is encoded into 16-bit instruction. So since whatever the ARM instruction set is there, the same instructions are compressed now. So now when your processor is running in a thumb instruction set, so each instruction, thumb instruction is going to be encoded into 16-bit instruction. Now if it is encoded into 16-bit instruction, how much memory location your each instruction is going to store? How many memory location it requires to store the thumb instruction? for one single instruction, since it is a 16-bit instruction. So how many memory location it requires? Any answers from your side? So it requires 2 memory location. So that's why we are going to have, so thumb instructions will run faster compared to the ARM instruction because it is using only 2 bytes of instruction. Since it is going to have the 2 bytes of instruction, when it is accessing the instruction, only 2 memory location it has to access. Whereas in your ARM instruction set, the same instruction it has to access in 4 memory location. So when it is accessing the 4 memory location, so there are some more operations has to be performed. So first, the request has to be placed on the bus. The bus has to request to the memory location. From the memory location, that instruction binary value is to be fetched from the memory to the processor. So the 4 times it has to access for a single instruction in your ARM instruction set, when your ARM processor is working in ARM instruction mode. Whereas the same thing, if you are working in thumb instruction set, it requires 2 memory location. So apart from this one, so your ARM core support instruction set extensions to enhance signal processing capabilities. So some of the cores are there in your ARM processor, so which will support the instruction set extensions to enhance signal processing capabilities. So it is signals instruction set extension is nothing but what? So you are going to have some coprocessor attached to your ARM, which has to support some of the other features like signal processing is there, like video card will be there in your system, or if you have the mobile also video, when you are going to have the high processing graphical unit, so even there you are going to have the video card, okay, inside that one. So when you want to access those features, it has to be accessed through core extensions. So you're going to have the set of extensions which we have discussed in the last module. So with the different features, I have to, with the help of the coprocessor, I will going to attach the coprocessor. So by using some of the instructions, I'm going to access that particular processor and I'm going to run. Okay. So now when it comes to the instructions, what are the different types of instruction your ARM is going to support is the next question. So as the instructions are classified, your ARM processor is classified into 3 ARM instructions or instruction set, what we are going to call. It is classified into 3 types. So what are the 3 types? One is data processing instruction, data transfer instruction, and control flow instruction. Okay, it is categorized into 3 types. One is your data process instruction, data transfer instruction, and control flow instruction. Okay, so next, another is conditional execution you are going to have. So since your control flow is nothing but your conditional execution. So first we will see what do you mean by conditional execution. So next, later we will come to know that what are the different data flow instructions you are going to have. So now in the conditional execution, so just I'm going through the basics of your instruction set. Okay. So in your conditional execution, what will happen is most instruction set allow branches to be executed conditionally. That means depending upon some condition. So assume you have the flags, right? So what are the different 4 flags we have studied? Any answers from your side? Whether you people remember what are the different 4 flags we have in your CPSR? So you have control current program status register. Under flag, we had 4 register. What are the different 4 registers we had? You have to read in your home. So you should not keep silent like this. So if you keep silent like this, then it will become difficult for you. So don't keep the habit of reading at the end of the exam only. So read daily. So this particular subject is not that much easy what you have been thinking. Okay. So here what will happen? So most of the instruction sets, it will allow branches to be executed conditionally. Okay. So here the most instruction sets allow branches to be executed conditionally. Now that condition, how it will be done? So that depends upon the flag status. The conditions what you are going to have, that depends upon the flag values. So we are going to have the condition flags, right? So what are the different condition flags you are going to have studied? We have gone through 4. That is N, which stands for negative, Z, which stands for zero flag, C, which stands for carry flag, B, which stands for overflow flag. So now whenever you are going to have like this, so however, by using a condition evaluation hardware, okay, ARM effectively increase the number of instructions. So if, depending upon the condition evaluation, what your ARM processor is going to do is, it is going to effectively increase number of instructions to be executed in a single clock cycle. Okay, as we have seen that the basic principle of risk design is what? In each clock cycle, one instruction has to be executed. That is what the basic design principle of risk philosophy, which we have gone through in your first module. So when you are running your one clock cycle, but due to some of the dependencies, it is not possible to run in a single clock cycle. Some more clock cycles it is going to take, due to the dependencies that you are going to study in those dependency in your future courses when you are higher, when you come to the higher semester. Okay, so all instructions which is I am going to have, it contains a condition field. So that particular condition field, that is going to determine you that whether the CPU will execute them or not. So whatever the CPU are going to have, that particular CPU will be having the condition field. That is nothing but your condition flags. That condition field is nothing but a condition flag in your CPSR register. That your current program status register. So that current program status register is the condition in the current program status register. What are the condition flags you are going to have? That will determine that whether that particular CPU will execute those branches or not. Okay. So now non-execution instruction in those things will also take up one clock cycle. Okay. So now why? Because even if it is not performing the operation, that particular instruction will be complete, has to execute and it has to stop. So when it is starting and stopping means what? Obviously it is going to take one clock cycle. So to allow the stages in the pipeline to complete. Okay. So because you are going to execute your ARM instruction in three different stages. If I take the ARM 7 instruction, okay, ARM 7 supports three-stage pipelining. That is your fetch, decode, execute. So now in a single clock cycle, what will happen? Either some one instruction will be fetching the data, fetching the instruction, other instruction will be decoding, third will be executing, right? So even if it is not executing, what will happen? The other instruction which is running in that particular clock cycle has to run. So for what that time, what will happen? Even the execution, it is not happening. It is going to consume one clock cycle. So that I has showed that one in example in the previous class, I think. So whether you remember that particular part, when you are going with the fetch decode stage for add, for example. So in the second stage, fetch will be happening at the second, for the second instruction, the fetch will be happening at the second stage. Wherever your first instruction will be executing the decode stage. Okay. So if you have some dependencies, that instruction won't be executed. That means it wants the data from the previous instruction. So since the previous instruction is not completed, I am not going to get the data. So then I have to stop. So if you are stopping means what? You are consuming some clock cycle. Okay. So for that particular reason, so it will allow other stages in the pipeline to complete. Okay. So what will happen? So when you are going with the conditional execution like this reduces the number of branches which will stall the pipeline. So that is what it does. So it is going to stall the pipeline. Stall the pipeline means what? It will stop executing for that particular clock cycle for that particular instruction. It will not stop all the instruction, but it will stop the instruction which is having the dependency. So now when you are going to stop for dependency, obviously in the real time also, if you take in the layman's definition, it is going to consume some time. So here also it is going to consume some time. The time penalty of not executing several conditional instructions is frequently less than whole rate of the branch of instruction. Okay. So that is what it is going to have. So next, condition codes, if we take some of the conditions code which we have discussed previously already. So now when you are going to have the condition code, the condition code will be having the block opcode. So opcode stands for operation code. OP stands for operation, COD stands for code. So opcode stands for operation code. So your operation code will be placing in the this particular condition code will be having from 28 to 31, right? So that is in your CPSR. So in your CPSR, what will happen? This particular flags condition code is placed in bit 28 to 31. So that is NZCV. You keep in your mind that 31st bit is N, second 30th bit is Z, that is zero flag. Your 29th bit is C, carry, and your 28th bit is V, which is overflow. So that you have to keep in mind. So that is NZCV. NZCV, you byte it. So that is will be a condition code. Okay, that is will be a flags. So next it is status and extension in your CPSR is kept for future use. After that one, you are going to have the control. Okay. So in the control, you are going to have interrupt, fast interrupt, and T, which stands for whether your ARM processor is executing the thumb instruction or ARM instruction, and then the mode of operation your processor is executing. Okay. So now here the hop code you can see depending upon the hop code. So you can see it is 0000. So if the opcode is 000 means what? Your negative flag is 0, your 0 flag is 0, carry flag is 0, and your overflow flag is 0. So then what is that particular extension stands for? A equal. Okay, equal. So equals 0. So when Z is set. So when Z is 1 and if your opcode is 0000, then it is going to set tell that you are going to have the 0 flag is set. Similarly, if it is having the not equal, so Z flag not equal means what? Your Z flag is 0. Z clear. You are going to have. So next is carry set is there. So when you are going to have the carry set, any answers? When you are going to have the carry set, which bit has to generate the carry if the carry has to set? Assume that I have the 8-bit operation. So assume you are going to have the 8-bit operation. Okay. Assume you are going to have the 8-bit operation. So but whatever the operation you are going to have here is a 32-bit. For your comfortable, I am telling it is a 8-bit. So now assume that I have 8-bit. Okay. Now, for example, if I am to add 80 plus 20. Okay. So the answer what you are supposed to get is 100. For example, I am telling. So like it will be 80H and 20H. So now here what it comes, it will be 1000. So here the carry won't be generated. Is 8. So it is 0000 80H. Okay. So now another 80H it will come. For example, I am telling. Okay. So you are going to have 1 0 0 0 0 0 0 0. So for example, what I will tell is it is 88 I will take now. So it is 88 and 88 I will take for your understanding purpose. It will reduce the confusion for you people. Okay. So now 88 if I take, now for example, so first I will take with the 0808. Then you will understand clearly. So if it is 0808, I will take. So if I take 0808, what will happen? The carry is generating from here. 1 plus 1 is 0. But carry is generated to the 5th bit. So it will be 1. Okay. Now, for this type of operation, your carry flag will be 0 only. Why? So, because the carry is not generated from bit number 8. Now, if we take 88 plus 88, what will happen? It is 0. So it is 0. It is 0. Now here it is 0 and it is 1. Your carry is 1 now. So if the carry is generated from 8-bit, if the carry is generated from 8-bit, then your carry flag is will be set to 1. So please note it down. If the carry is generated from the MSB, general statement I am making. So if you are doing the 16-bit operation where the carry is generated, if the carry flag is to set
16th position.
Yeah. So if the if you are doing the 16-bit operation, then if the carry is generating in 16-bit, then your carry flag will be set. So if you are doing the 32-bit operation, if the carry is generating in 31st bit, then the carry flag will be set to 1. So that means you have to meet. That way is going to mean. So next, it is carry set is there. So like CS is the mnemonic extension you have to give. So when you are going to have the carry clear is there, that will make you make your carry flag to clear, that is 0. Okay, unset, that is a minus or negative. So when you are going to have the negative, when the negative flag is set, so that is n flag is set. So positive when you are going to have, so when your n flag is clear, so when the n flag is clear, so it is a positive value which you are going to have. So overflow set means what? You are going to have the overflow. That means whatever the register you are going to have, so that particular register are not able to store the maximum value. So when you are going to have that particular kind of scenario, the overflow will be there. So if you are going to have the no overflow, so we clear. Okay. So next you are going to have unsigned IR. So unsigned IR, it is coming when you are using the unsigned operation. So that is nothing but what? So if you are taking the signed operation, in the signed operation, it will be having both negative value as well as the positive value. Whereas if you take the unsigned operation, it is going to have only the positive value. It doesn't have the unsigned value. So that you have to keep in your mind. And whenever the unsigned comes into the picture, it doesn't have any negative value. It will be having only positive value. So only when you are going to operate on the unsigned value, signed value, you are going to have the negative values. Okay. So that's what it means. So next is when you are going to have the mnemonic as HI along the instruction. So HI along the instruction is nothing but what? So sometimes what will happen? I want to do like this, it will be having. Okay, for some conditions I'm going to have. For take add equal. So if I take add equal, EQ is what? EQ is mnemonic for to tell that whatever the previous operation it is going to have. So that has generated the 0 flag. That means the previous result obtained is 0. Whether you are doing the subtraction or whether you are doing the division or whether you are doing the multiplication, that is left to you. But whatever the value it is going to have, so that has obtained the 0 result. So when you are going to have the result only, I have to perform the operation. If not, I'm going to perform the operation. Okay, for example, add equals R2 comma R1 comma R0 I am going to have. This particular instruction is going to execute only if your 0 flag is equal to 1. So only if 0 flag is 1, this particular instruction will be executed. So it is executing the random instruction is going to execute only if it is equal. If it is equal means what? It will look into the 0 flag. If the 0 flag is set, then only this particular instruction will be executed. If your 0 flag is not set, in the sequence of execution, this particular instruction won't be executed. In the sequence of execution, this particular instruction won't be executed. So this is what it means. Okay. So next, similarly, you're going to have signed less than, signed greater than, signed always. So this you understand whenever the program comes. Okay. So it is just a simple example. Okay. What is an example of a conditional execution? Now here, you can see it. So an unusual feature of the ARM instruction set is that conditional execution applies not only to branches, but to all ARM instructions. So it is not only to branch you are going to have, even for the different instructions also that particular works. So you're going to have the compare instruction first. So in the compare instruction is nothing but it is using only to set the condition flags. Keep in your mind that your CMP instruction is going to be used only to set your condition flags. That you have to keep in your mind. So whenever you want to set the flags, what you have to do? First, you have to write. You have to execute the compare instruction. So when you do the compare instruction, it will be R0 comma R5. For example, I'm doing. So what it will do is it will subtract R0 minus 5. That whatever the value which is stored in R0. So then it will be subtracted with 5. So now, if branch equals means what? So if branch equals means what? Say if R0 is the value contents of the R0 is 5. Then you have to go for bypass. So when your R naught equals 5, then you have to go for bypass. So if your R naught is not 5, what I need to do? So add the value of R1 and R naught. So compare, initially you compare that. So R naught, let the value of R naught be 1, for example, or 0, for example, I'm going to have, or 1 you take it. So now when you are going to have the 1, so I'm going to have R naught 1. So it is checking with the condition with 1 comma 5. So whether your zero flag is set? No. So it is going to do 1 minus 5. So 1 minus 5 is minus 4. So when you are going to have the minus 4, what will happen? So branch equal, it will check. So when it is going to branch equal, whether it is equal? No. So if it is not equal, so what it will do? If it is equal, where it has to go? It has to go for bypass. It has to jump. It should not execute these two instructions in the middle. If it is not equal, what I need to do? I will add the contents of R1 and R1 and I will store the result in R1. Okay. So next I'm going to subtract this particular instruction also executed. So then it is coming for bypass once again. And again the sequence of instruction will start again here. Okay. So this is how it will be executed. So now, depending upon these things, whenever the conditional sequence is 3 instructions or fewer, it is better to exploit conditional execution than to use a branch. So some of the times what happens, conditional sequence you are going to have in 3 instructions. You are going to apply for 3 different instructions has to be there. So at that time, what will happen is you have to exploit the conditional execution without having the branch instruction. So B gives a branch instruction. If you are going to have the conditional is 3 instructions or fewer, it is more or less than 3 instructions are there. So then it is better to make use of the execution exploit conditional execution in the instruction itself. Okay, what it means, so you are going to compare here with respect to R0 and R1. Instead of that one, I am going to compare equal. That means what? If you are both, if the previous result is not 0, then only I am going to compare it. So if a previous result is 0, then I am going to compare the next instruction. If the previous instruction is not encounter 0, then I am not going to execute this particular instruction. That means that one. So if it is equal means what? It will compare R2 minus R3. Add equals means what? If the previous instruction are is executed in 0 value, then I am going to add it. So if not, it is not going to add that one. Okay. So it is similar to your what we can tell. So I mean, if you want to find the first n numbers, find the sum of first n numbers. For example, if you have, we will take that example and we will write it in the next class. Then you will understand that how it will be used. Okay. So anybody having any doubt till now? Anybody having any doubt? So these are the 2 different simple examples which you are going to have. Okay. So anybody having any doubt now till now? So if E is equal to, if take this particular example, here you have the example is what? If A equals B and C equals D, E plus plus. Okay, first I am going to compare the values of R0 and R1. So your R0 have the value of variable A, your R1 will be having the value of B. First it is going to compare. So now, after that one, what I need to check? I need to compare with the equal. So if it is equal, what it will be generated? It will be generating the 0, right? This particular equation will be generating the 0. So next, if it is 0 only, it will execute the C equals D. Okay. So if not, it will come out. Okay. So if it is executing to 0, if both are equal, then which instruction it has to execute? It has to execute the compare equal to instruction, because it has to satisfy both the condition here. So if A equals B and C equals D, then I have to increment the value of variable E. So that means what? I'm going to have the instruction compare first. I'm comparing with what instruction? I'm comparing with A equals B. So once you have the instruction A is equal to B, here what will happen? First compare R0 comma R1. So if it is equal, what will happen? Your 0 flag will be set. Then again I have to compare what? Again I have to compare the value of C and D. Again I have to compare the value of C and D. So when you are comparing the value of C and D, what will happen? So now again it is R2 and R3. So which is having the holding the value of C and D. Now again if it is equal to 0, if a value of C and D equals to 0, then what it has to execute? It has to execute the value E plus plus. If both are not satisfied, what it has to execute? You should not execute both. First it will compare 0 comma R0 comma R1. So if it is encountering 0, then only this particular instruction will be executing. So now again, if it is not satisfying, this instruction won't be executed. Again, if it is not executed, even this particular instruction won't be executing. Okay, it will sequence now. You understood now? Anybody having any doubt? Anybody having any doubt with respect to this particular instruction?
No, sir.
Okay, you understood, right? So just only thing how you are going to understand is you write one simple C code. The corresponding C code, you write the instructions there by the side. They will understand that how to write the assembly code. So this is how I'm going to teach you. So don't worry about that one when you're writing a program. So it will be easy for you to understand at that time. Okay. So I will stop here now. So we'll discuss about the more instructions in the next class. ಹೋಯ್ತು ಲ್ಯಾಪ್ಟಾಪ್ ಅನ್ಸುತ್ತೆ ಲ್ಯಾಪ್ಟಾಪ್ ಹೋಯ್ತು ಅನ್ಸುತ್ತೆ ಏನು ಅಂದ್ರೆ ಪವನ್ ಯೂಸ್ ಮಾಡ್ಬೇಕು ಪವನ್ ಯೂಸ್ ಮಾಡ್ಬೇಕು
ಹಳೆ ಲ್ಯಾಪ್ಟಾಪ್ ಹಾಕೈತಿಲ್ಲ ನಿಮ್ದು ಹಳೆ ಲ್ಯಾಪ್ಟಾಪ್ ಅಲ್ಲಿ ಯೂಸ್ ಮಾಡಿ ಹಳೆ ಲ್ಯಾಪ್ಟಾಪ್ ಯಾರು ಯೂಸ್ ಮಾಡ್ತೀವಿ